So we're going to look at effective substrate concentration and effective enzyme concentration on rate of reaction. This is important. You can talk. Okay, you can ask questions. It's because you're being recorded. I'll just edit it out afterwards. Right, so I think I said to you early on about the importance of just recognizing what graph it is that we're looking at. So we have sort of, now our default is that we have, what we've seen so far is temperature along the bottom and rate of reaction up the side. We've also seen pH along the bottom and rate of reaction up the side. This is the thing you need to keep your eye on, okay? So to begin with, it's okay, we're going to do substrate concentration. So what we're going to do is we're going to carry out, so we'll picture we're doing this as an experiment. Remember what I said before, that even though we may say something like, as substrate concentration increases, as temperature increases, we are not gradually increasing the temperature on one test tube, if you like. What we're doing is we're carrying out an experiment at a lower temperature, and then a higher temperature, and a higher temperature, and a higher temperature. And we're getting some data from that, individual items of data, and we join them together. And that's what gives us our graph of temperature that does that. So we have to set the scene to begin with. So this is now, this reaction is taking place, we'll say then, in a test tube. And in that test tube, we're going to have a number of enzyme molecules. And that is going to be a control variable, i.e. the concentration of enzyme molecules will be constant, and what we're going to change is substrate concentration. So we're going to start with a very low substrate concentration. So how fast does the reaction proceed then? And then we're going to increase the substrate concentration and see what that does. So we'll start down here with the substrate concentration of 0. So if I put a value of 0 there for substrate concentration and a rate of reaction of 0 there, not that I necessarily have to put values there on a sketch graph, I'm just making that distinction. If you do a graph, you definitely do have to put values there. I think actually, when you do a sketch graph, I think it used to be part of the old practice, you do have to put, when you do a sketch graph, you have to put full titles on units. And I think they do ask you to do an origin, but kind of that doesn't really apply now. But the idea is here that if we have a substrate concentration of 0, so we put no substrate in there, and then we see, well, how fast is the reaction going to proceed? Clearly we're going to get no reaction, and consequently a substrate concentration of 0 results in a rate of reaction of 0. Now if I was to continue this graph, show the shape of this graph, probably the logic thing we'll say is that what will happen is you increase substrate concentration. What will happen? What will happen to rate of reaction? It will increase. Okay, and that's the logical thing to say. Well, if I add substrate, the reaction can actually happen. And the more substrate I add, the more the reaction can happen, i.e. the faster it will go. So indeed, we do get that shape. For substrate concentration increasing, yes, rate of reaction increases. But it doesn't continue like that indefinitely, it levels off. So we've got two real sections of this graph that need explaining. We have this section here, the slope section, okay, what's going on there? Why is it that as I increase substrate concentration, rate of reaction increases? And then from there on, or why is it that even though I continue to increase substrate concentration, rate of reaction no longer increases? So this bit here should be straightforward, and that drawing, visualizing this is useful. So this bit should be straightforward. Well, if I put one substrate molecule in, this is always, however, it's limited because enzymes convert substrate to product, and then the enzyme is free to do its job again. It's not a case of we match up one enzyme with one product and say, oh, sorry, one enzyme with one substrate, and then say, well, that's as fast as it can go. No, because an enzyme will break down a substrate very, very quickly and can catalyze the reaction with another substrate immediately. But in general terms, if I just add a bit of substrate, yeah, nice one. Add a bit more substrate, we expect that to go twice as fast. 3 times as fast, 4 times as fast, 5 times as fast, because there's enzyme there that's available to do the job. The issue comes when I put, let's go to the extreme, and I put so many substrates in that if I was to imagine I was freezing this and there's no reaction taking place at all, and suddenly I go, go. Well, the enzyme will indeed work on the substrate straight away, but at time 0 or just after 0, every one of those enzymes will be catalyzed in this reaction with the substrate, and some substrate molecules will not be catalyzed. Well, that reaction won't be catalyzed. They're waiting. The analogy is often given with like in a well, I say post office, but shops where you have a certain number of cashiers, and so if you think of the cashiers as being, and so let's say you've got the post office where you've got 6 places for cashiers to be, and 3 of them are occupied, or there are 3 people in those 6 places where cashiers can be. And then you've got 1 person coming into the post office, and that's great, they get seen straight away. And in fact, 2 people coming in, brilliant, they can both be seen at the same time. And 3 people, they can both be seen, they can all be seen at the same time. 4 people though creates a problem. 4 people creates a queue. So the first one goes to 1, to 2, to 3. The 4th person has to wait, and there's a queue. And we've effectively reached the fastest rate that people can be processed. There are only 3 people there. That's what determines how fast we can go. That's the maximum rate. So I said there are 4 going in, there's 1 in the queue. If 4 million go in, doesn't make any difference to the speed though, does it? Because they can only deal with 1 at a time, and there are only 3 of them. Consequently, the only way you can actually increase the rate of reaction when you're looking at substrate concentration, or at that point there, where they're all working to maximum capacity, is to do what? That is quite a tricky question. Thanks for listening. The only, once we get to this point here, whereby we're at a particular substrate concentration above which it can't go any faster, this is our maximum rate. There is only one way we can, okay, there's one perhaps more obvious way that we can make that maximum rate increase. Okay, so both of those are valid, both things are, temperature would indeed probably do that, it would increase the rate of reaction, but actually concentration of enzyme is what I was trying to get at, because it's a case of increasing, the analogy would be, okay, you've got 3 people, 3 cashiers, let's have a 4th one, and now that can go, whatever it is, 30% faster, and then let's have a 5th one, they can, as a team, they can work faster again, because there's more people doing it, and they can get through that queue quicker. The rate at which they get through that queue would be quicker. So that's the explanation really, but we just need, as I did before with temperature, there's certain marking points, certain sort of waypoints we need to hit. So like I said, there's 2 sort of sections here. We kind of ignore this because it gets very complex. We've got this section here, the sloping section, which is, so as substrate concentration increases, rate of reaction increases. And the Y, clear distinction needs to be made that you have enzyme active sites are available. So at any one time, anywhere along here really, okay, so I'll say that first, anywhere along this graph, these substrate concentrations, at any snapshot in time, when you look at those reactions, there will be 3 enzyme active sites. It does not mean there are more enzymes than substrates. It doesn't necessarily mean that. Remember what happens with an enzyme. It will form an enzyme-substrate complex, form a product, will dissociate, and then it's free to carry out another reaction. In order for this to be working at its maximum rate, the time taken for an enzyme to find a new substrate after it's just carried out one reaction is pretty much 0. I.e. there's so much substrate in there, by the time the enzyme's done, done that job, just turn around, there we go, another one, and it's straight in there. Now, that needs more than a 1-to-1 ratio of enzyme to substrate. I can't give you a value, but it's sort of more like 1,000 to 1 of substrate to enzyme. So 1,000 more substrates than enzyme. Then as soon as the enzyme's carried out its job of one substrate, immediately there's another substrate occupying its active site. So it doesn't have to be, but it's common to think of, so imagine we've got, I said like 3 cashiers. Okay, let's say 5 cashiers. We put one substrate in. And then we put another, so that's down here, and another substrate in. So if I looked at that point then, so there's one substrate, 2 substrates, cannot really work in terms of single things, but the analogy works okay. So one substrate, yeah, it goes faster than when we had no substrates. So, oh yeah, it goes faster, twice as fast. But you see, well, why is it that it continues to go upwards? Because look, there are enzymes available. And key, we need to say there are enzyme active sites available. So when I add more substrate, oh yeah, it goes faster. And I add more substrate, yeah, it goes faster. And it goes faster. When I continue add substrate from there, now there's a queue. And so we don't have that clear distinction of, oh look, that very straight line upwards of saying, look, it's a very linear relationship here. At the top, so I'm glossing over this, at the top, what we've got is a number of substrates there. So as what I'm doing from there, every time I add one of these, I'm moving this way more, I'm adding more substrate. Every time I do that, it goes further and further and further. Doesn't make a difference. They're doing what they can do. They can't work any faster than that. So what do we say? All enzyme active sites are occupied. So, in theory, we could make this go faster. This is our theoretical max right now. Okay, this here you can read across from here. So at the moment, this is the maximum rate of reaction that could be achieved. We could increase that by adding some more enzymes. Not an unlikely question. Add more enzyme. Okay, we're now saying, well, if they're all working to their full capacity, this one slots in there. Yep, it can be moved up higher. We can get that theoretical max to move up higher. It would end up being a graph that does that. But our key waypoints are that this, to be honest, this graph is not that common that we see this because it's a bit too easy. What we have to deal with is what happens when we include inhibitors, and that will use this as a starting point. So, okay, you remember this graph? Okay, now we're going to add an inhibitor in, and that's quite a common one to see. Okay, right. Let's change that now. Okay, we're going to change this from substrate concentration to enzyme concentration. So this is asking the question, what happens when we increase enzyme concentration to the rate of reaction? Okay, so can you give me a logical answer to that? If I increase enzyme concentration, what will happen to the rate of reaction? Yeah, okay. Tell me why that may not be true. Under what circumstances are we not going to see that? Oh, you're close. Just not quite. You're very close to that. It's related to that. It's to do with the substrate quantity. Yeah, I want to say it like that. What will happen eventually to the substrate? It will alter into product. And so that graph is valid on the assumption that we have massively excess substrate. So that graph is valid if we say, do you know what? We have to work in terms of, I said an infinite concentration of substrate. I mean, then it becomes theoretical, but it would be valid with an infinite concentration of substrate. Yes, that is correct. That's exactly what it should be. You very rarely see that. Largely because, for that reason, I suppose, like what would happen if you did have I don't know how to do this, but if you did have a limit to the substrate, well, this is true that as you increase enzyme concentration, increase enzyme concentration, rate of reaction will increase. But let's go to an extreme and say, imagine we've got, I don't know, Well, let's say we've got more enzyme than substrate. More enzyme molecules than substrate. What's the rate of reaction going to be there? It's a bit of a trick question, so that gives you an idea. More enzyme than substrate. What's the rate of reaction going to be? If I say we've got 1,000 times more enzyme than substrate, realistically, what's the rate of reaction going to be there? Okay, yeah, you're on the right lines, Ella, but I'm talking about, I want to know what happens here. At that point there, massive amounts of enzyme, relatively little substrate. What's the rate of reaction going to be? What you told me was the whole graph, and you're right with the shape you said. What's the rate of reaction going to be at there? For every one enzyme molecule, there's, one substrate molecule, there's 1,000 enzyme molecules.
It's just going to level off, because it's not going to really...
Won't level. I'm asking you to give me, that's what makes, you said, well, hang on, how could I possibly give a value to that?
It would take enough time for one substrate to be catalyzed. I don't know what that is.
Yeah, so how long would it take to be over? Like nothing. So if you try to measure that, your rate would be 0. It's over. It's immediately over. So anything you try to measure, so you wouldn't be able to. So Ella said, so the graph would look something like this. Yeah, but I get very, I can understand that, and I can understand that what happens here, I just don't know how you would draw that. It's something like that. Do you know what though? You'll never be asked this because of the complexity of that. You might, I've never seen the question, how does enzyme concentration affect rate of reaction? Assume an excess substrate, yeah, fine. But that's not the question they ask. And so this is our segue now into, let's change the graph. So we're now moving, for the first time, we're moving away from rate of reaction. And we're now moving to amount of product produced. Now, first thing, alarm bell should be ringing really. Why? Because I've said amount, how dare you? Yeah, absolutely. Because this is a generic thing. So the amount could be the volume of a gas produced. It could be the concentration of some product produced, whatever. We're not specifying that, so it has to be overly vague. So it's amount of product produced. And then, this changes as well. We have time along the bottom. So first of all, what will this graph look like? That's quite tricky. Why is that? Because you're looking down.
Yeah, in the notes.
Okay, so why will it look like that?
Because, well, at the start...
So what Nick said is this. It's going to look like that.
Yeah, so because at the start, when you're carrying out the experiment, at the start, most of the reactions are going to occur. But then, when you move longer throughout the reaction, there's not going to be enough active sites of the substrate unless you're at...
active sites of the enzyme, you mean?
Yeah, sorry.
Yeah.
There's not going to be enough. So the amount produced will just level off.
You went in and out of the right answer there. You went in and out, you said, yeah, okay, yeah, and then you lost it a bit. What describe what's going on? Describe what's going on first of all. So we start with...
It's going to increase at the start.
What will? You need to say
the
what?
amount the product produced at the start of the experiment will increase, but will then level off after a certain amount of time.
Okay, so as time proceeds, the amount of product produced will increase, and there will come a time where it levels off. So first of all, why will it level off? Yeah. All the substrate converted into product, so there's no substrate left, the reaction's over, absolutely right. So really this reflects, that's the end of the reaction, that reflects, that's all that's all the substrate that was there, so that's all the product that we can actually make. This is talking about enzyme concentration, we haven't done that yet. This is our starting point. This is a standard time versus amount of product produced. This is what we see. What does this gradient reflect? Yeah, that gradient there, whatever calculation you get from that, that's the rate of the reaction. Okay, if I say this is a high enzyme concentration, remember this is square brackets as shorthand for concentration, what's a low enzyme concentration going to look like? So tell me, what will it do if I put a lower enzyme concentration in? What will that do to the rate? So the rate is slower, okay? So if you said this is a measure of rate, so you're right, we're going to be lower down here.
Will it level off at the same point though?
So why will it level off at the same point?
Because it's still the same amount of substrate, but it's just slower to get to the point.
Absolutely right. Absolutely right. It will get there in the end. It will just take longer. You're like, oh my God. So, with a low enzyme concentration, the amount of product that is produced in the end will be the same. It just takes longer. It's pretty logical. It's pretty, you know, if you revert to the analogy of the people in the post office, the cashiers in the post office, if you reduce the number of cashiers, they'll get through the queue. They'll get there in the end. If they try and get through 300 people, yeah, they'll get there. It will just take longer. Doesn't mean they can't do it. The same thing applies here. This is a common one we see now. This is more like what you'd be expected to see. So they'll give you a graph and they will say things like, okay, what would be the effect of having a lower concentration or a higher concentration of enzyme? And common, when we look at inhibitors, so everything there spot on. Okay, indeed an even higher concentration of enzyme, we know it's gonna be steeper and level off sooner. Okay, that's a logical thing to extract from there. Be careful, when we talk about inhibitors, we do have graphs which do not look like this. We might have the same type of thing. We do see graphs which do that. So it's very common when this graph is, people are asked this, lower concentration of enzyme, then end up drawing this. And you've just, you all got that idea. I just said, well, we'll get through it. The reason why people make those mistakes is because they don't zone in on this and say, what is the graph I'm dealing with here? This is time versus amount of product produced. The one where we see that is actually substrate concentration versus rate. Not today, but when we introduce inhibitors, we go back to substrate concentration versus rate, which is what I implied. And then we do see a difference which looks like that. So you've just got to be on the ball with your graphs. What we will do in time is, I think there's about 15 graphs that I'll say, right, explain to me please, or draw on the graph, what would be the effect of, and your first, okay, what's going on? And then, okay, what's the change being made? And there's about 15, 16 graphs, something like that. So, okay, now do that to it, now do that, now do that. And that's actually not that bad. The issue is then when you're given one in an exam, you've just got to zone in on the right thing. Okay? Any questions on that? Let's get you doing some